Hi everyone, today I will walk you through our data analysis and modeling process. First, let's talk about exploratory data analysis or EDA. After loading and extracting the dataset, we found that the data quality was quite good. There were no missing values and no duplicate records. We then used auto visualization to explore the data further. And the data and the auto visualization help us identify several data quality issues, such as outliers, rare categories, and high correlations between some features. Regarding outliers, their impact is partly reduced when we use tree-based models like random forest and GBM. Since these models are naturally most robust to extreme values. However, for logistic regression, outliers can still have a noticeable impact, especially if the features are not properly scaled. For rare categories, if they are not grouped or handled properly, they are treated as equally important as frequent categories. This can introduce noise and reduce model stability, particularly for linear models. As for highly correlated features, we consider using PCA to adjust multicollinearity because PCA transforms correlated variables into a smaller set of uncorrelated components. Next is data preprocessing. For categorical variables, we apply label encoding, which converts each category into an integer. This method is simple and computationally efficient, and it allows us to use categorical features directly in machine learning models. However, a limitation of label encoding is that it may introduce an artificial order between categories, which can be misleading for models like a logistic regression. We also examine the skewness of numerical features. All numerical variables show Y-skew distributions, meaning the mean is larger than the median. Some features were highly skewed. For example, most individuals have no children, while only a small proportion has more than three. This large number of zero values results in high skewness for the number of children feature. Adjusting Y skewness can make the data distribution more symmetric, which helps improve model stability and training performance, especially for linear models. That said, skewness transformation may reduce interpretability and usually has limited impact on tree-based models. We also explore principal component analysis or PCA. We found that after about 15 components, the cumulative explained variance increased slowly based on the feature's importance result. The top four important features were years employed, age, total income, and account length. Then we compared different pre-processing strategies to choose a better encoding method. We compare label encoding and binary encoding, use model accuracy on the test set. For logistic regression, there was no difference in accuracy between the two methods. However, for random forest, label encoding performed better, so we choose label encoding overall. We also tested whether clustering should improve model performance. We applied k-means clustering and added the cluster labels to both logistic regression and random forest models. The results shows that no improvement for logistic regressions, and performance actually decreased for random forest. Therefore, we decided not to use clustering. For model selection, we then use H2O auto machine learning. Based, based on the auto ML leaderboard, GBM5 was selected as the final model. Because the GBM5 achieved the highest AUC, which was about 0.5729. We choose AUC as the main evaluation metric because it measures how well the model distinguishes between classes across different thresholds and is more robust than accuracy when class imbalance exists. Although some XGBoost models show higher accuracy and precision, their lower AUC scores indicating weaker overall class discrimination. Therefore, GBM5 provided the best balance between performance and robustness. Finally, here are some possible improvements and suggestions. First, model evaluation could be improved by using cross-validation instead of a single train test split. This will give a more reliable estimate of model performance. Second, class imbalance could be adjusted more explicitly by using methods such as class weighting, smooth, or threshold tuning. From a business perspective, our results suggest that customer risks and behavior are driven by nonlinear patterns and complex feature interactions. Therefore, ABC Bank should consider using advanced ensemble models like gradient boosting for risk assessment and decision making. In addition, the analysis highlights the importance of data quality and feature engineering. Better preprocessing, such as handling skill variables and rare categories, can significantly improve model reliability. Finally, model evaluation should go beyond accuracy. Since the costs of false positive and false negative are different in practice, ABC Bank should focus more on metrics like AUC, recall, or cost-sensitive measures and adjust decision thresholds based on business goals. Thank you for listening.